Thank you for that kind introduction, and thank you for everybody who came. So like Chung Chef said, I'm here to talk about the work that we recently did on higher order Newton methods. This was joint work with Amir Ali Ahmadi and Abrar Chaudhry, who are at Princeton and Georgia Tech respectively. So if you knew about the work, you probably saw it from one of these three places. Don't worry if you can't read what's on the bottom here. I can't either, but I think that it's been kind that people have spread this work. So let's just start with the basics. What is Newton's method? So the idea is that this is an iterative algorithm, and the way we're going to proceed is that if we have some function we want to minimize, feel free to think of this as like a loss function or loss landscape. But we want to minimize this, and at any given iteration, we form the second order Taylor expansion, minimize that, and that's our new iterate. So this is just an example in the univariate case. As you can see, it's forming new parabolas, and the method just moves to each of those parabolas. For something in a higher dimension, it would look something like this. So again, you have some function you want to minimize. You form the second order Taylor expansion, and then you move to the minimum of that Taylor expansion. So the Newton iterate, it just looks like this. Again, I'm forming the second order Taylor expansion. Anytime we have a Taylor expansion in this talk, we're going to go ahead and call it phi. So we form the second order Taylor expansion. This, of course, gives us a quadratic polynomial. And then we just minimize that. It's a quadratic polynomial. It has a really nice closed form. And it's that closed form that one of the things that makes Newton's method really desirable and pretty much like omnipresent in optimization. And if you know of Newton's method, you probably also know that it has quadratic convergence, which says that under certain conditions, namely that you have some Lipschitz continuity conditions, and you're close enough to a local minimum, then you're going to have quadratic convergence to that local minimum. And again, this along with the fact that we can compute these iterations really easily are what makes Newton's method really desirable. So there are limitations to Newton's method, of course. So again, it doesn't always work. If you're not close enough to a global minimum, then you can have issues. If you want to construct a lot of examples, just pick pretty much anything with an S-shaped gradient. The picture shown here is Newton's method for root finding, but that's essentially equivalent to using Newton's method for optimization. And you can pretty much see that anytime you have this S-shaped gradient, if you start too far away from the minimum, then your iterates are actually going to go farther away from the minimum as you go. And then you have other issues like stability. So what I've pictured here are what are called Newton fractals. So the idea behind a Newton fractal is I pick some grid of points. In this case, it's in two-dimensional space. And then from each point in that grid, I start Newton's method and see where it converges to. And then I colored any given point based on the point it converges to. And this is a good way to visualize the stability, or in the case of Newton's method, often the instability of Newton's method. You can visualize where it converges, where it doesn't, and then you can observe that there's a lot of unpredictable behavior you can get if you just use Newton's method. So the idea of using higher order information in Newton's method isn't new. At least for 300 years, people have been thinking about how to use higher order information in Newton's method. And at least in the univariate case, it's possible to do this. And of course, the idea is that if you have more derivative information, you can get better approximations of the function you want to minimize. So, for example, can you guys see the laser pointer, by the way?
Yes, yes.
Okay. So we have a function here that we're trying to minimize, and also what I've drawn are the second order Taylor expansion down here, and the third order Taylor expansion down there. So you can see that the third order Taylor expansion does give you a much better approximation of the function, and that translates into faster convergence and better basins of attraction. So for example, the basin of attraction here is somewhere, of this function is somewhere out here. If I had started Newton's method from over here, it would actually not converge to the global minimum. And again, this is a perfectly well-behaved looking function. It's convex. It's something that you might think would be nice to minimize, but in fact, it's not. And again, I've drawn some more Newton fractals here that sort of demonstrate the instability you can get with Newton's method. Um, in this case, the blue points, or the yellow is good here. Yellow are the ones that converge to the global minimum, and then blue is the ones that don't. And even though, like, you could argue that you have more yellow here in total, the fact that the yellow region here is this nice contiguous figure means that by using higher order information, you can actually get like more stability. So why haven't we done this? And the simple answer is that optimizing high degree polynomials are hard. And this was actually a lot of the work I did during my PhD that was looking at essentially the complexity of local minimization. Of course, if you were to try to use higher order Newton methods, you need to be able to minimize high degree polynomials because, of course, these Taylor expansions of higher degree are higher degree polynomials. But, informally, pretty much anything in polynomial optimization is NP hard once you get to degree equals 4. I've listed a non-exhaustive list of problems that become hard. So for example, globally minimizing a polynomial, locally minimizing, uh, finding a second order point, and even finding a critical point. So the first one here was known for quite some time. The last three were done during my PhD. And I think I should have also mentioned that deciding whether a function is convex is actually also hard once you get to degree equals 4. So this idea of, um, convex might be easier. You could have an issue if you can't even tell a function is convex. So I did want to spend some time talking about some intermediate work that kind of bridges what existed to what eventually became our work on higher order Newton methods. And really what it comes down to is if we could minimize high degree approximations, we could make Newton methods out of them. That's the bottom line. So for example, something that I did previously was show that finding local minima of cubic polynomials is actually a semi-definite program. Um, Now, cubic polynomials, of course, don't actually have global minima. They're odd degree polynomials, so they will go down to minus infinity, but they can have a local minimum, and you can actually find it using semi-definite programming. And if you actually try to implement this, you would actually get something really similar to what exists for a regular Newton's method. So if you were to make an algorithm that constructs the third order Taylor expansion and then moves to the next iteration using semi-definite programming, then you would essentially get an algorithm that yields a theorem like this, where you're pretty much, getting an equivalent result to the quadratic convergence, except this is cubic convergence. As you can see, I've basically replaced all the 2's by 3's, and that's kind of the idea that you can do better with more information. As for something that a lot of people have looked at, one of the most common frameworks is this thing called the convex regularized Newton's method. So really what this is again, I've taken the standard Taylor approximation here, and I add this regularization term. And the idea behind this regularization term is if I pick the constant out in front in a particular way, and in particular it's going to depend on the Lipschitz constant of the dth derivative, then this function is actually always going to be convex. And, what people have hoped is that, again, convex optimization is generally seen as easier. So if you have something convex, maybe we can actually minimize it. And Nesterov actually did come up with something for d equals 3. They get global convergence out of it at a linear rate. There is the issue that you don't know how to find L, so like a priori, there's not any particular reason to believe that you know what the Lipschitz constant of any particular function is. So that's actually something that makes a little bit of a gap in terms of making this implementable. And actually being able to pick the constant in this regularization term is a big part of what makes our algorithm work. So are there any questions so far about this? Is just an introduction so far. Okay. So this is the outline. I'm going to begin with an introduction to something called sum of squares because sum of squares is really the crux of what makes our algorithm possible. Then I'm going to present the main ideas of some of the proofs. I'm going to hand wave a lot because otherwise it's just like, messing around with constants when I really just want to get the main idea of the proof across, and then we're going to talk about some examples. So what's a sum of squares? So we're going to be dealing exclusively with polynomials when we talk about sum of squares. So a polynomial is a sum of squares if it can be written as a sum of squares of other polynomials. So for example, if I have some polynomial p, I want to be able to write it as the sum of a bunch of qi squared. And there's really two things that make sum of squares of interest to the optimization community. It's easy to show that such a polynomial is always globally non-negative, of course, because you're adding a bunch of squared terms. It's always going to be like that. And then also the really thing that makes it interesting to the optimization community is that you can decide whether a polynomial is a sum of squares with semidefinite programming. The idea is that you can extract the sum of squares decomposition out of any positive semidefinite matrix, and you can also optimize over the set of sum of squares polynomials. So how do people use this in optimization? What they use this for is for finding lower bounds for the optimal value of optimization problems. So I want you to imagine you want to minimize a function f, and in terms of at least the optimal value, I want to argue that it's equivalent to maximizing gamma, such that f of x minus gamma is a non-negative polynomial. So the idea is that, if I look at what f of x minus gamma is doing, what that's doing is I take the x-axis here and I'm essentially moving it up and down based on what gamma is. And the idea is I can move gamma basically all the way up to the point of where the global minimum of f is. So if I move it up or maybe down to where the global minimum of f is, the most I can move that is to the what the global minimum is if I want f of x minus gamma to be a non-negative polynomial. So again, you know, general optimization's hard, so there's no reason to be that we should be able to expect to minimize this problem. But what the idea behind sum of squares is that this constraint that f of x is a non-negative polynomial. If I replace that constraint with f of x minus gamma as a sum of squares polynomial, that is now a semi-definite program. So this problem, maximize gamma such that f of x minus gamma is a sum of squares, is actually something that we can do. Now, of course, because sum of squares polynomials is only a subset of the space of non-negative polynomials, we do have to replace this equal sign with a greater than sign, but there's questions about when it's exact, but at the end of the day, this is kind of the core behind uh, sum of squares optimization. And there's extensions for constrained optimization. I'm going to briefly mention them, but uh, we're mostly going to be looking at unconstrained problems here. So what's actually what we use in the paper? Something called sum of squares convexity. So we say that a polynomial is sum of squares convex. If this polynomial you can write oh wait, no, this is a typo. There should be a Hessian there. But it should be y transpose the Hessian of p times y is a sum of squares polynomial. Where does this characterization come from? Well, if you have a convex polynomial, then its Hessian is always going to be positive semidefinite. And one of the characterizations of positive semidefinite matrices is that y transpose times the matrix times y is non-negative for any y. So if you say, non-negative for any x and y, that should basically be somewhere that you can replace being non-negative with being a sum of squares. And that's exactly what sum of squares convexity is. So again, because telling whether a polynomial is sum of squares convex reduces to deciding if a polynomial that you can write down is a sum of squares. Deciding SOS convexity is also something that we can do with a semi-definite program. And I do want to mention that there are other analogs of sum of squares convexity that are all equivalent. So for example, there's a characterization that comes from the first order condition. You can make one out of like the Cholesky condition, and then you can make one out of the geometric definition of convexity. They all give other ways of writing down a definition of sum of squares convexity that all end up actually being equivalent. So the main ingredient, the other primary ingredient we need is this idea that of minimizing sum of squares polynomials. And this is actually from Lasserre. So what I've written here is a polynomial optimization problem. So this is just I'm minimizing some polynomial subject to some polynomial constraints. And if I write out the first order Lasserre relaxation, it looks something like this. And what we actually need is that if you can write down your polynomial optimization problems using entirely SOS convex polynomials, then we can actually minimize the problem exactly with sum of squares relaxations. And moreover, we can actually get the solution to the SDP. And again, what's pictured here is the constrained version. What we need is the unconstrained version. But the key takeaway here is that we can minimize SOS convex polynomials. So, going back to this idea that if you have a way of minimizing high degree polynomials, you can make an algorithm out of it. And this is kind of the key thing that we needed to make the algorithm work. So before I talk about the convergence, are there any questions? All right, moving on then. So again, the main idea is that we want to leverage SOS convexity. And we're going to take the ideas behind SOS convexity and put them into the framework of convex regularized Newton's method. So this is the informal statement of our algorithm. Again, what the convex regularized Newton's method seeks to do is it takes a Taylor expansion and adds a regularization term. And something that I mentioned is that the coefficient in front of the regularization term is not actually something that's entirely trivial to find because it depends on a Lipschitz constant that we shouldn't expect to know what it is. So what we do is we're going to find that with semidefinite programming. Now, the idea again behind using this regularization term is we want to make our approximation convex. What we do in our method is we want to make this approximation SOS convex. And the reason this is better is because I described previously that we actually can't detect convexity for high degree polynomials. However, we can detect SOS convexity. So what we do is say, all right, let's add a regularization term. Instead of making it convex, we're going to ask for a little more. We want it to be SOS convex. And once we have that, as I described previously, we actually can minimize SOS convex polynomials. And from that, you basically have your algorithm. You compute your Taylor expansion, you compute the exact coefficient on the regularization term that you need, and then you minimize the approximation. So what this thing over here is saying is that's just a fancy way of saying the next even number that is higher than d. The reason we need this is because sum of squares techniques really only work with polynomials. If you add a odd degree regularizer, you no longer have a polynomial, which is why this needs to be even degree. And the goal in this section is to show that eventually we can get another convergence guarantee that looks like what you have for Newton's algorithm. So, Newton's algorithm would be if I had these d's as 2's, but because we're using higher order information, our goal is going to get stronger guarantees. Now, this is an algorithm. If we were in, say, like machine learning, we would, have this algorithm and call it a day. We're mathematicians, so we're going to make sure we cross our I's and dot our T's. So we have a little to-do checklist to do. So we want to show that this coefficient that we want in front of the regularization term exists. And as long as it exists, we can find it. We do need it to be finite. The second thing we need to do is show that our approximation has a well-defined minimum. And finally, we're going to show the convergence. So just showing that the SOS convex approximation exists. Essentially, the idea is you have this convex regularizer, and you need to argue that, if you added a big enough regularizer, then eventually it would be SOS convex. And intuitively that should be the case. Intuitively, you might expect that, as long as you're going above this Lipschitz constant, then that should be enough. And that kind of is the argument. So what we did is we need to show that you have this polynomial that's in the interior of the SOS convex cone. And once you have that, you can make this argument that, you know, if you blow up the coefficient in front of the regularizer, then eventually it will be big enough that your polynomial is SOS convex. And the reason this works is a more general statement about cones. So you should imagine that this cone is um, the set of sum of squares convex polynomials. You have you have this function here that's in the interior, and then you have any other polynomial, and there is some convex combination of these two that lies inside the cone of SOS convex polynomials, and then you can kind of back out what alpha needs to be based on that. So, so we know that we can actually find the coefficient to put in front of the regularization term. The next thing we need to do is argue that it has a unique global minimum. And what we showed is that for a convex polynomial, if its Hessian is ever positive definite, then it has a unique global minimum. This is a rather technical lemma that actually turns out to be super important for the convergence proof too. And it involves essentially integrating polynomials over a line. It says that if we're integrating the Hessian of a function and it's ever positive definite, then the integral along that line is also going to be positive definite. And how you use this lemma to prove this function is you say, all right, you do this integration, you always get something positive definite, so then you know that you can lower bound on any line with a quadratic function. And this is a uniform bound. And then you argue that, okay, you can lower bound it with a positive definite quadratic, so it must be coercive, and if it's coercive, it can't have multiple global minima because otherwise it would have to be constant along that line. And because our regularizer is convex, we can just go ahead and apply this lemma. And as for the intuition behind why this works, essentially the idea is that with a very particular quadrature, you can interpolate the integration of any d-degree polynomials with particularly chosen d points. And this is true no matter what your polynomial is. You can always do this interpolation with the same interpolation points and the same weight on each of those points, no matter what your polynomial is. So now that we've crossed our I's and dotted our T's a little, let's move on to the convergence proof. And I'm going to start with a little bit of warm-up, which is just I'm going to reprove the quadratic convergence of regular Newton's method. This proof again is very old. I'm sure it's done a lot of times, and I'm sure the proof I present here is really nothing new, but I just wanted to present the ideas that we used for our proof. So you start with the Newton iteration that looks something like this. And the reason I don't like this is because you would never really get to a proof for higher order Newton's method if you started with this. The reason is because you're not going to have a closed form solution if you're looking at higher degree polynomials. So instead, we're just going to start with the optimality condition. And this is just saying that the Hessian times xk plus 1 minus xk plus the gradient equals 0. I haven't really done anything yet. You do a few manipulations and you get exactly the Newton iteration out. So I haven't done anything yet. What I do is add an x star and subtract it. Most proofs of Newton's method do this anyways. And the reason we do this is because we want to essentially pull out a particular term. So what's this term on the right here? This is actually the approximation of the gradient at x star. So x star is the global minimum, and you separate it out into two terms. One that's the approximation of the gradient at x star, and some other term that looks like this. And the important thing about this term on the right is it has xk plus 1 minus x star, which is eventually where we want to get to because our whole goal is to be able to bound the norm of this particular vector. And again, there's some like being close to the global minimum thing that I'm hand waving away. You essentially use that to argue that this matrix is positive definite. And then the other thing you need to hand wave away with close enough to the global minimum argument is that this isn't too far away from zero. The lemma we're going to use essentially says that if you have some Lipschitz continuous polynomial, then, given a particular order Taylor expansion, you can actually bound exactly how far away any particular Taylor expansion is from the function itself. So in this particular case, if we're looking at the Taylor expansion of degree 2, it'll be some far away from the actual gradient at x star. So, you replace this with 0. This is this term here. And then the constant in the front, we don't really need it too much. That's just a constant. And then this degree becomes 2. And if you put that all together, then you get, this bound here, which you should recognize as just saying that quadratic Newton's method has quadratic convergence. So does this make sense?
Mm-hmm.
Okay, perfect. So we're going to take this and we're going to generalize it. So again, we're starting with the first order condition for optimality. So we're going to write out generally what this looks like. So we're just saying, let's take the degree d Taylor expansion centered around xk. And at xk plus 1, which is the next iterate, that gradient should be 0. So the key step behind why this proof works is, again, we decomposed it into two terms. One that looks like the gradient at x star and something that depends on xk plus 1 minus x star. So in order to do that, we're going to do something like this. So this is the gradient of the degree d order Taylor expansion at x star, and we're just going to add and subtract it. So I haven't done anything here other than like I really wanted to introduce this term into the proof. So, again, we said, all right, this is the approximation of the gradient at x star using the lemma I had on the previous slide. And again, hand waving most of the details, but we can argue that this quantity is going to be small. And now we want to say something about this quantity on the left. It has something there, right? You can see that there's an xk minus 1 and an x star, so maybe we can work with that. And it turns out again that you can, and we're actually going to use that same lemma we had before based on quadratures because, well, we were looking at the gradient, and of course the gradient is just the integral of the Hessian. So essentially what you're doing is this is just your integral of the Hessian going from xk plus 1 to x star. You can where we just got to was we had this term that was the difference of two gradients. We replaced that with the integral of a Hessian. And the main observation is that if we use this lemma on the right, because we're integrating some matrix that we know is positive definite, we integrate this matrix, we're going to get something positive definite. Uh, and this is xk plus 1 minus x star, which is what we wanted in the first place. So essentially, by doing this transformation and applying this lemma, we basically got everything that we wanted. Um, so just as a recap, we have a matrix that we can argue is positive definite times xk plus 1 minus x star plus the approximation of the gradient at x star. So the idea is I'm going to move this over to the right, multiply the inverse, and that's basically where the convergence rate comes from. So we do need to cross our I's and dot our T's a little more because the proof that I just talked about didn't have the regularization term in there, but really what it comes down to is that because it's convex, we need to tweak that integral, but because this is convex and all we really needed for the proof to work was this quantity inside the integral was always a positive semi-definite, then we didn't really have to change our proof that much. And so essentially the proof still goes through. So in summary, essentially we have some matrix M, which is that big giant integral matrix that I had before. We have some matrix M times xk plus 1 minus x star is equal to the gradient of the Taylor expansion at x star. We go ahead and move this to the right, multiply by M inverse, apply some Lipschitz continuity lemmas, and then the fact that M is positive definite, and then we get what we desired, which is that uh, we have ordered deconvergence. This is actually a typo. That needs to say xk minus x star. So are there questions on the proof? I know that proof kind of got broken into two sections there. Yeah, so I'm just stopping to ask for questions because uh, this is a typo, but this really just wraps up the convergence proof if you replace this with xk minus x star. All right, then just going to move on to some numerical examples. So what does this look like in the univariate setting? So if you go back to what the geometric interpretation of Newton's method is essentially you're doing root finding on the gradient. This is Newton's method for root finding. You bump everything up one order of differentiation, and that's how you basically get regular Newton's method. So for dimension d equals 3, essentially what you're doing is you have some gradient, and instead of just approximating your gradient with a line, you are approximating with a parabola, or maybe not even a parabola, you might be approximating it with a cubic function. And if you do this in dimension 1, you can actually work out exactly what the next iterate is. It looks something like this, which is pretty messy, but in univariate, you can always just do like, say, bisection methods or something like that. Here's another example. This is a function square root of x squared plus 1 minus 1. And if you try to use Newton's method on this, you kind of run into a similar issue with what I described at the beginning of the talk, which is you have this S-shaped derivative on the derivative, which means that if you try to use Newton's method on it, it's not going to work super well. But if you apply higher order Newton methods, you still do a little bit better. So again, this is just a plot. The function is in blue, the second order Taylor expansion is in orange, and this yellow is the third order Taylor expansion. This does get a lot closer if you use more derivative information. For this particular function, the basin of attraction for regular Newton's method only goes up to 1. If you go higher, it goes up to 3.4. And if you use more information, then this keeps going up and up. And the reason that Newton's method has a rough time with this particular function is it basically gets linear towards the end. So you can imagine if you drew the approximation here, it basically looks like a line that shoots all the way to the other side of the x-axis. Another example, this is just another function that is perfectly well behaved and convex, except its gradient has that S shape. You can run the third order Newton method, compare it to how fast the classical Newton's method runs. The third order Newton's method is going to be much faster. This is a way to visualize what the convergence looks like. So this essentially is saying if I start Newton's method at any particular x, what is the next Newton iterate going to be? So what this graph actually shows is that if you start Newton's method outside of the basin of attraction, which is this 1.712, you end up converging to this point here, which is x is about 13, but that our algorithm actually has global convergence. Kind of the way you would see it from this graph is that because this blue curve is below this black line here and above the black line here, that's how you can argue that it has global convergence. So an example in 2 dimensions, this is the Beal function. It's non-convex and it's just a problem that people look at when they're evaluating optimization functions. I think I already showed you this Newton fractal before. This Newton fractal actually comes from the Beal function when you apply just regular Newton's method as opposed to the third order Newton's method. And again, the thing to see here is that you get a lot more stability when you're applying the Newton's method with higher order information. And the last thing I wanted to mention for this talk is that basically all of our results were local. We talked about the local convergence of our algorithm. You can make a small tweak to it that gets you global convergence. So in a scenario where you do know the Lipschitz constant of the function you're trying to minimize, essentially you could apply this convex regularized framework where you actually know exactly what coefficient to put out in front. Of course, in our algorithm, you picked this coefficient based on the solution to an SDP. If we knew what the Lipschitz constant to use is, we would just take whatever is higher between what our SDP told us to use and the Lipschitz constant that we knew. Now, there's a slight tweak that you need to do. In the convex regularized framework, you basically just go 1 degree up, but you could, there's nothing stopping you from going 2 degrees up if D was even in the first place. So that's the end of the talk. A bit of a hiccups in the middle, but we got to the end. Thanks for listening, and I would be happy to answer any questions.